Here in part A, we have to find out the voltage gain of a given circuit. So in order to find out the voltage gain, we need to draw a small signal equivalent circuit of the following figure. Here plus or minus Vi, this is the gate terminal, RF feedback resistor is the drain terminal, RDS drain to source resistance, minus plus mu Vi equals to mu VGS. This is the source terminal, load resistance between drain and source, this is Z in, here is Z out. Now the voltage gain AV equals to VDS by Vi, which is equals to RL RDS 1 minus RF GM divided by RF RDS plus RL RDS plus RL RF. If we substitute the data given in the problem, we will get minus 10.35, which is option A is true. Regarding part B, in order to find the input impedance in the following circuit, we need to apply the KVL in the input loop, which is equals to Vi equals to II RF plus VDS. VDS equals to AV into Vi, which is a voltage gain which we calculated in the part A. Now if we substitute equation 2 in equation 1, we will get Z in as follows: RF by 1 minus AV. After substituting the data given, we are going to get 1320 kilo ohms, which is option D is true.
Is the transfer function of a feedback control system is given, and that is T of S equal 50k by S power 4 plus 20s cube plus 15s square plus 2s plus k. Now he is asking find the range of k such that the system is stable. Now a system is described by a transfer function that is given in the problem. Now he is asking whether the system is stable or not, and find the value of the k such that the system is stable. Now we have to find out the value of k such that the system is stable. That means here it is a conditionally stable system. So that means if the condition is true, then only the system is stable. Otherwise the system is not stable. So that's why we have to find out the condition for system stability here, right? So to find out the system stability, first we have to find out the transfer function, right? The transfer function is directly given here, so that's why our work is simplified. So here, and next, after finding the transfer function, we have to find out the characteristic equation of a system. Now what is the characteristic equation? If you find out the transfer function, the denominator part is nothing but a characteristic equation. Here the denominator is S power 4 plus 20s cube plus 15s square plus 2s plus k. This is equal to 0. Now this is our characteristic equation. After finding the characteristic equation, then the next step is we have to find out the Routh-Hurwitz criterion. In the Routh-Hurwitz criterion, we have to find out a table. Now the table indicates S power 4, S cube, S square, and S power 1 and S power 0. Right, here the S power 4 means 1 multiplication factor, and then we have to look for S square. S square multiplication is 15, and then S power 0. S power 0 multiplication factor is k. Right, after that S cube multiplication factor, that is 20, and then S multiplication factor, that is 2. Now then we have to find out all these rows, and after that we have to decide the system stability condition. Now this will be 30 minus 2 by 20. 30 minus 2 by 20, because 20 15 300, sorry, 300 minus 2 by 20. Now this will be k, and after finding that we have to find out s power 1 coefficient, and s power 1 coefficient is this 300 minus 2 by 20, and this will be 14.9. and after that we have to find out s power 1 coefficient. So here we have to fill up this row. So this row is 14.9 multiplied by 2 minus k by minus 20k, sorry, by 14.9. Now this coefficient will be 0, and again this coefficient is k. Now to decide the system stable or not, here, okay, for deciding that, if you observe the first column of the Routh-Hurwitz criterion, that should be all positive coefficient. If you get the positive coefficient, then the system will be stable. Now 1, this is a positive, and 20, this is also positive. Now here 14.9, this is also positive, and if you come to s power 1, here the 14.9 into 2 minus 20k, this should be positive. This should be positive means what? The 14.9 into 2 minus 20k should be greater than 0, then only this is positive, and s power 0 coefficient is k, so this is also positive. That means what? K should be greater than 0. Now these are the two conditions. If you satisfy these two conditions, then we say that the system is stable. Now find out the condition here, right? If you solve for this, we will get k equal 14.9 into 2 by 20. So that means we will get 1.49. So that means if k is less than 1.49, then the system is stable. So the marginal value of the k marginal value is 1.49 that we got. Now if the k is less than 1.49, the system is stable. And also one more condition is there. If k is greater than 0, then the system is stable. If you couple these two conditions, now our option will be D, 0 less than k less than 1.49.